We have looked at the simplex method and the different methods involved in simplex, like the dual simplex method, the big M method. Now, in a situation where the constraints are too many, we know that the time taken to solve the problem will be higher. So in such a case, you can convert the linear programming problem to its dual problem, which requires relatively lesser time to solve. So the aim of this lesson is just to introduce you to the dual concept. First of all, you have to formulate a dual problem, then you have to apply the duality concept in problem solving. So what you can see here is just the general format of a premium linear programming problem. This is what we've been dealing with. You can be given a maximization or minimization problem. You know that this is the objective function and these are your constraints. Your constraints can have less than or equal to sign, or equal to or greater than or equal to sign. Now, if you want to form a dual problem, you've been given an example here where you have to form the dual the premium problem. So it depends with the problem that you'll be given. If it's a maximization, minimization, the type of the sign that you have on your constraints, everything will change when you want to formulate a dual problem. So I'm going to give you just different examples so that you see how the problems change from the premium problem to the dual problem. Now, when you want to formulate these problems, first of all, you have to know the number of variables in the premium and in the dual problem. So the number of variables in the dual problem will be equal to the number of constraints in the premium problem. That is when you are formulating the objective function. And then for the constraints, the number of constraints in the dual problem will be equal to the number of variables in the premium problem. So let's take a look at what we have. This is a maximization problem. So if we had to form a dual problem, we have to turn this into a minimization problem. This will become a minimization problem where z will be equal to, z will get the values for the right hand side of the constraints. So these are the values 25, 30 and 40. So z will be equal to 25. Then you introduce y, where y is the dual variable associated with the ith constraint of the premium problem. You have 25 y1 plus 30 y2 plus 40 y3. Then this is chapter 2. Put your constraints. The first constraint will have the values of the first variables, which is x1. All these values for the first for the variables x1, 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 these will appear in the first constraint. You have 2 y1 plus 4 y2 plus 6 y3, and this, because it's a minimization problem, the sign will be greater than or equal to. And then you get the first number here for the objective function. So on the right hand side you have 4 for the first constraint. Then you go to the next constraint, you pick these values 4, 9, 8. You have 4y1 plus 9y2 plus 8y3 greater than or equal to. You get the next number here on the objective function, 10. Go to the next one, this and that. You have 8y1 plus 8y2 plus 2y3 greater than or equal to 25. We always have to indicate the fact that y1, y2 and y3 will be greater than or equal to 0. We restrict our sign. This is in a situation where the sign is restricted. So in this case, the sign is going to be restricted. And there are other situations where we have unrestricted sign. Okay, so this means we can indicate that y1, y2, and y3 are unrestricted in sign. But for such a case, we have a restriction. So it's as simple as that. Let's go to the next problem. Let's look at a different example. This is example 2. Example 2 involves a minimization problem. Minimize z equal to 20x1 plus 40x2. And then this is subject to the constraint 2x1 plus 20x2 greater than or equal to 40. 20x1 plus 3x2 greater than or equal to 20. 4x1 plus 15x2 greater than or equal to 30. x1 and x2 are greater than or equal to 0. So, like I said, the number of variables in the dual problem will be equal to the number of constraints in the premium problem for the objective function. So you can see that here we have three constraints. So the number of variables in the objective function will be 3. You have in the solution maximize. So when it's minimization, we change it to maximization. We say maximize z equal to 40 y1 plus 20 y2 plus 30 y3. I'm getting them from these values 40, 20 and 30. Then subject to, you know what will happen. The first constraints will have 20, we have 2, 20 and 4. So this is 2y1 plus 20y2 plus 4y3, and then less or equal to, so this is less or equal to, as you can see here we have 20, less or equal to 20. Then the next one will be this one, to be 20y1 plus 3y2 plus 15y3, then less or equal to 40. So like I was saying, the number of constraints in the dual problem will be equal to the number of variables in the premium problem. So you have seen that this is exactly what has happened. And you have to include the fact that y1 and y2 should be positive, greater or equal to 0. So this is your dual problem, very easy to formulate. Just you knowing exactly when to, if it's a maximization problem, how it's going to change. It's going to be minimization. If it's minimization, it's going to be maximization. And then how the signs are going to change. So now what happens in a situation where you want to get the dual of the dual? Dual of the dual. Let's take a look at what will happen using this same example. Okay, so this is maximize z equal to 40y1 plus 20y2 plus 30y3. If we had to change it, it would be minimize z equal to, so we look at the number of variables that we have in our constraints. There are 2. This is 20 and 40, so this will be z equal to 20 x1 plus 40 x2. Then let's take a look at our constraints. They will be subject to, the first constraint will be 2x1 plus, so if this time we're using x1 and x2, so there will be 2x1 and 20x2. 2x1 plus 20x2, and then greater than or equal to 40. In the second case, we have 20x1 plus 3x2 greater than or equal to 20. Then the last one will be 4x1 plus 15x2 greater than or equal to 30. So you can see that we are going back to the actual problem, which was this one here. So we have gone back to this problem. As you can see, everything is the same. So this means that the dual of the dual will give you back the premium problem. You are going back. So that's something that you need to know. Sometimes you might want to prove if your solution is correct, so you can always go back. Now let's take a look at the situation where you have equal to sign. Your constraints have equal to sign. What happens in that case? So you have been given to maximize z equal to 4x1 plus 10x2 plus 25x3. Maximize z equal to 4x1 plus 10x2 plus 25x3 subject to 2x1 plus 4x2 plus 8x3 equal to 25, 4x1 plus 9x2 plus 8x3 equal to 30, 6x1 plus 8x2 plus 2x3 equal to 40. x1, x2 and x3 are greater than or equal to 0. In this case, you have to turn this situation the same way. You have to turn it into a minimization problem. So this will be minimize z equal to, so you can see that we have 25, 30 and 40. So you have 25 y1 plus 30 y2 plus 40 y3, and then this will be subject to, this is the minimization problem. So you have greater than or equal to sign. You have 2y1 plus 4y2 plus 6y3. The first constraint, 2y1 plus 4y2 plus 6y3 greater than or equal to 4. Then 4y1 plus 9y2 plus 8y3 greater than or equal to 10. So this is coming from this, the second column here. And then this is the value that you get on the right hand side. Then the next one will be 8y1, 8y2 and 2y3. 8y1 plus 8y2 plus 2y3 greater than or equal to 25. So you have to explain here that y1, y2 and y3 are unrestricted in sign. Does not matter what sign they will have. They are unrestricted because we had equal to. The constraints had the sign equal to. That's how you formulate the dual. Another example is when you have to minimize, say z equal to 5x1 plus 8x2. Then this is subject to 4x1 plus 9x2 greater than or equal to 100, 2x1 plus x2 less or equal to 20, and then 2x1 plus 5x2 greater than or equal to 120. You can see that we have different signs in our constraints. Let me not forget this. Here we have less or equal to. So you have to change this because this is a minimization problem. You have to change it. You have to make sure that the sign here is greater than or equal to. What do you do to change the sign? You have to multiply by -1. So you multiply by -1 to get this problem. Minimize z equal to 5x1 plus 8x2, then subject to 4x1 plus 9x2 greater than or equal to 100. So I've just picked it as it is. The first one is this one because it has greater than or equal to sign, so it's fine. But the next one we'll have to multiply by -1. Let me do that. So to this one we multiply by -1. So here on the 2 you have -2. You have -2x1, and you have minus x2, and then this will be greater than or equal to, and then -20. Then the next one is just going to be the same because it has greater than or equal to sign. So you have 2x1 plus 5x2, 2x1 plus 5x2 greater than or equal to 120. x1 and x2 are greater than or equal to 0. Now we can easily write this into its equivalent dual problem. This will just be maximize z equal to, so you see that how many number of constraints do we have? We have 3 number of constraints. So this will be equal to the number of variables in the dual problem for the objective function. You have 100 y1 plus, no, this is negative, as you can see. So you have -20 y2, and then you have plus 120 y3. Oh, let me just rewrite this. Maximize z equal to 100 y1, then here minus 20 y2, then plus 120 y3. This is subject to, you have 4, the first one, y1, and then the next one minus 2 y2, and then plus 2 y3 less or equal to, this one here is 5. Then the last one is 9 y1, then minus y2, which is this one, and then the last one is 5 y3, and then less or equal to 8, which is this one. Then you can indicate that these are greater than or equal to 0. So that's how you go about forming the dual problems. So we can now go to application. How do you apply the dual problems? Application of dual problems. So you can see that here when you have a very, you have a lot of constraints. There are 2 constraints here. There are 3 constraints, and then in the dual problem the constraints have reduced to 2. So this is the importance of forming the dual problem. It helps you when you come to solving using the simplex method. An example. So let's look at an example. Example is solve the following LPP problem using the result of its dual problem. Minimize z equal to 24x1 plus 30x2 subject to 2x1 plus 3x2 greater than or equal to 10, 4x1 plus 9x2 greater than or equal to 15, 6x1 plus 6x2 greater than or equal to 20, and then x1 and x2 are greater than or equal to 0. So you have to form the dual problem. That's the first step. Form the dual problem. This will become a maximization problem. To maximize z equal to, you can see that we have 3 decision variables, so the number of values in the objective function will be 3. We have 10y1 plus 15y2 plus 20y3. These will be subject to we have how many values in the objective function? We have only 2, so you expect to have only 2 constraints. You have 2 y1 in the first constraint plus 4y2 plus 6y3. This will be less than or equal to 24. And next you have 3y1 plus 9y2 plus 6y3 less or equal to 30. Then you can indicate that your variables should be greater than or equal to 0. Then you can easily put this in a simplex table. So you have to put this in a simplex table. The initial table as we know it. Here you have basic variables. How many basic variables do we have? So before we even go to the table, we have to write this. We have to introduce our slack variables. So we have to write it in a canonical form, because now it's already in standard form, so we have to introduce the slack variables. So we introduce the 3 slack variables. No, there will be 2 slack variables, s1 and s2, because you see that we have 2 constraints. So you have minimize z equal to 10y1 plus 15y2 plus 20y3 plus 0s1 plus 0s2. Just getting this. And then subject to the constraints: 2y1 plus 4y2 plus 6y3 plus s1 equal to 24, 3y1 plus 9y2 plus 6y3 plus s2 equal to 30. Then all these should be greater than or equal to 0. Now we can form the table. So this is the table which has CJ, CBI, has basic variables, it has solution and ratio. And we know the basic variables that we have: y1, y2, y3. So maybe they are too spaced. y1, y2, y3, s1 and s2. Then this is 10, 15, 20, 0 and 0. Then you can close this up. We have s1 and s2, these are zeros. Then you have 2, 4, 6, 1 and 0, 3, 9, 6, 0 and 1. Solution is 24 and 30. And then we can form Zj and Cj minus Zj. So Zj here will just be 0, 0, 0, 0, 0. And then 10, 15, 20, 0, 0. And then this is 0. So we can see that we have not reached the optimality condition. So we go through the iterations as usual, where you get the highest number here for Cj minus Zj, forming the key column, and then you get the key row from the ratios. 24 divided by 6 gives you 4. 30 divided by 6 gives you 5. And then you have this as your key row. Then you start the iterations. So I'm sure if you've seen the other videos, this is going to be easy for you. So you can get the iterations and then you can get your answers. So your answers here, for those who want to prove, you can get the values of y3 to be 2, y1 will be 6, and then y2 will be 0, and z will be equal to 100. So that's all on duality and application. Thank you for watching.